Yep. Okay, so let's go for a collision. So we're going to collision of the ping pong ball fast, or not so slow. That's the 2 meters per second job, and 30 grams. And brick, which is going to be the fast brick. So 2 meters per second. No, I've got something wrong here, haven't I? The ping pong ball was 50, that's right. And 2 meters per second and 2 kgs. Okay, so we're going to do that. We're going to do that combination of things. Okay, so we know from our previous calculations that this one has a momentum of, that was the ping pong ball, that's that one, 1.5. And this one has a momentum of 4. Yep. Okay, so let's draw a picture. So I assume when you say collide, you mean head-on collisions. It's not that the brick's moving and the ping pong ball catches up with it. So we've got the ping pong ball going this way at 50 meters per second. That's a ping pong ball. And we've got the brick going that way at 2 meters per second. And they're going to smack into each other. And what's going to happen when they smack into each other? Okay, so do you want the ping pong ball to bounce off? You don't want the ping pong ball to crumple and stick on the brick. You want them to actually bounce off and go back. Okay, so how fast is the ping pong ball going to bounce off, do you reckon? It was going in at 50 meters per second. It hits the brick and it bounces back at 100 meters per second. 48? 48? Okay, 48. So it's slow. It's comes back slightly slow. This is number, so Levi's given us 48 meters per second. So it goes back out at 48 meters per second. 100? 100? Okay. 50? It depends on a whole lot of things. So we haven't actually got enough information to know what the answer is. It depends on what's called coefficient of restitution. So basically how bouncy the things are. If this wasn't a ping pong ball, if this was a lump of putty that was thrown at the brick, same mass, same speed, a lump of putty is probably going to stick onto the brick, whereas a ping pong ball will bounce. So it depends on things we don't know all about as to how much. So any of these figures are possible. So there's no right answer. Yeah, well, we're just doing just the moment of collision, just for the before to after. So yeah, it would. If it further away, it would. So the speed it bounces back with will depend on the contact between the brick and the ball. So any numbers that you're suggesting are all reasonable. So let's go for one that we can calculate a bit easier with. Let's go for, say, 70. That's a reasonable number. So it's picked up a bit of speed. It's going back the other way after it's been smacked by the brick. Okay, so the question is, if that happens, what happens to the brick? It'll just be slightly. Will it slow down a bit or speed up a bit? Okay, so because the mass of the brick is so big, it'll only slow down a little bit, is the idea? Okay. Yeah. But if you threw a ball fast enough at a car, would it slow the car? Would it stop the car?
Oh, no, that's probably no.
You should read. There's a. I assume you've all seen that website. If you haven't and you want to be engineers, you should, because it's genius. And he asked the question, how many something you have to use to slow down a train? That I don't think it's ping pong balls. It's something, maybe just shotguns or something to stop an express train. And it's the same sort of idea. Yeah, well, or speed. Yeah, maybe. Yeah. So let's do that. We can actually do the calculation, and figure out what happens to the brick. Okay. So what we're using here is what's called the idea of conservation of momentum. Okay, that's the big idea for this whole lesson. So what it says is that the total momentum before the collision is the same as the total momentum after the collision. So if we know what the momentum is beforehand, which we do because we've got these two momentums, we can figure out what the total momentum is, and then we can say it'll be the same afterwards. So beforehand, we know the momentum of the ball is 1.5, and the momentum of the brick is 4. So what's the total momentum before the collision? 5.5 from Zane. Anybody got anything else? 2.5 from Nick. 6 from Glenn. 6.5 from Ricky. Any advances? Okay, so we're going to have a way of figuring out who's got this right. So who wants to justify their number? Where's your 5.5 come from, Zane? You just plus the two numbers? Yep. No, it's going to be the same afterwards. So whatever it is beforehand, it'll be the same afterwards. So the question is, what is the momentum before? So you came to 5.5 just by adding those two numbers. Glenn, how'd you get 6? You timed them, so that one times that one to give yourself 6. That's fair and legit. Nick, what'd you do?
Because I've gone 2 different ways, I
Okay, so Nick's basically saying it's vector addition. So the direction should matter, which I think is what I want. I want, if they were both going in the same direction and you had to stop both of them, it would be more than if you had to stop one going each direction. So I'm with Nick. So the total momentum beforehand is 2.5 kilogram meters per second in that direction. Yep, total, because it's 4 that way, 1.5 back that way, so we're left with 2 going that way. That's the total momentum the together that they have. Yeah, makes sense? And now we've got to figure out what's going on afterwards. So what we know afterwards is that the total is the same. Yep, so the total momentum afterwards is the same as it is before. That's what conservation of momentum means. Which means we know how fast our ping pong ball is going, so we can figure out momentum of the ping pong ball afterwards. So this is before and this is after. So our afterwards is 70 meters per second times 0.03, which is 2.1, I think, isn't it? Is that right? Does that sound right? 70 times 0.3 is 2.1 kilogram meters per second. Yeah, you happy? All happy with that? So all I've said is momentum of the ping pong ball afterwards is just mass times velocity. The mass is still 30 grams times the velocity is now 70, gives us 2.1 kilogram meters per second. Yeah. So what's the mass of the brick after? Or what's the momentum of the brick afterwards? 0.4. In which direction, Scott? That way. So it's still going that way, isn't it? Yep. Because this 2.1 we've now decided is that way. We need a total of 2.5 that way. This gives us 2.1, so we need an extra 0.4 that way. And then from that, we can work out the speed of the brick. So we use momentum as mass times velocity. Bit of rearranging, velocity is momentum divided by mass. 0.4 divided by mass of 2 is 0.2 meters per second. So our ping pong ball has slowed the brick down from 2 meters per second to 0.2 of a meter per second. So the ping pong ball will actually have changed the mass, the speed of the brick quite a lot in this case. Okay, so Liam's raised the idea of an elastic collision, which we'll come to in a second. Okay. Yeah, so I don't think you can judge that just by looking at that. It might not be, but we'll come to it. The 70 meters per second we got because Levi said 48 and Ricky said 100 and Scott said, oh, let's choose something in the middle. So I did. Okay, so that was a number we just made up. It depends, like I said, it would depend on the nature of the two things colliding. So if it was a piece of putty, then it would have probably stuck to the brick. And it wouldn't have bounced back at all. That had gone together. Okay, so this is a really standard process, conservation of momentum. So calculate the momentum beforehand and the momentum afterwards, and then you've got enough information, you should be able to work out the velocity of whatever's going on afterwards.